Hello and welcome to the third part of Lesson 6. In this lesson so far, we've introduced the energy equation and what it physically means, along with a workflow to solve it. We examined some non-dimensional groups, some of which provide justification to simplify the energy equation for specific problems. What we're going to do now is systematically follow this workflow to solve the energy equation for a film casting problem. Once we've set the problem up, we're going to look at 3 different heat transfer cases so that we can see the various ways in which we can manipulate the energy equation to arrive at the equation we need to solve through each step of the solutions. 2 of these solutions are straightforward. 1 is a little more involved. For this latter solution, I've provided a document on Canvas that shows the steps that need to be taken. So, let's start by reminding ourselves of the workflow that we've developed to solve heat transfer problems. So here on the whiteboard is a reminder of that workflow. There were 4 steps in this workflow. The first, arguably most important step was sit down and think about the problem. Draw a diagram. Identify the modes of heat transfer. Create that mental model so you really understand what's going on, to the point where you're pretty sure what the answer is going to be, and the rest of the problem-solving process is just proving what you know already. If you get a different answer to what you think you knew, that is a time to really step back and say, well, have I solved the right problem? Is there an error in my solution? Or was there an initial error in my understanding? And if there's an error in your understanding, you need to really sit back and think about why that's the case and what it is that you haven't taken into account. So the second step was to decide on a number of heat transfer dimensions, 1D, 2D, 3D, to simplify the mathematics. The third step was to choose a coordinate system that adequately describes the problem that you're solving. And the fourth step was to use your boundary conditions to figure out whether you've got constant temperature at a point in your heat transfer problem or constant heat flux at other points in the same heat transfer problem. Hopefully what we're going to end up with by the end of this workflow is a nice, easy equation that we can solve analytically. It's not always the case. Sometimes, in fact very often, we have to solve these equations numerically, and we're going to be talking about a lot more next lesson. So for now, what we're going to do is to examine some one-dimensional problems so we can get some nice simple solutions. And the process that we're going to look at is film casting, or sheet casting, because it's actually going to be quite a thick film. So, as I inferred at the beginning, we're going to look at 3 different heat transfer scenarios. 1 is trivial. 2 are a little more involved, but in each case we're going to sit down and think about what we're going to expect, what physical scenario these problems correspond to, and then check at the end whether what we've calculated marries up with what we expected in the first instance. So let's understand the heat transfer problem that we are dealing with. Let's sit down, let's draw a diagram, and let's really think about it. So there on the whiteboard is my highly simplified, slightly unorthodox film or sheet casting problem. So I've got an extruder. There's hot stuff coming out the extruder, and then I've got a quenching airflow rather than chill rollers. And the reason I've chosen the quenching airflow rather than chill rollers is because it illustrates better the different heat transfer modes that I want to get across. So you can imagine this is a thick film or a sheet, and that we've got this quench airflow and then some take-up rollers. So I am wanting to determine the temperature profile in this sheet between the die exit of the extruder and my take-up rollers. So I'm going to draw a diagram of the modes of heat transfer in this sheet or in this film. So there on the whiteboard, I've zoomed in on my film. That red box is my little control volume, and it corresponds to a point in the film arbitrarily placed between the die exit and my rollers. So let's think what's going on. So I've got a quench airflow. Okay, that infers I'm going to have heat transfer off the film surface by forced convection. Okay, so that's one mode of heat transfer I need to incorporate. I've got material coming from an extruder being taken up by pickup rollers. So my film is moving. Or there may be some cases where my film is moving. So that infers I've got advective heat transfer going on. So if I'm thinking about what else might be happening, I've got thermal conduction potentially happening as well. And that could be happening across the thickness of the film, in the convection direction, or across the length of the film, between the die and the take-up rollers. I'm going to neglect heat transfer by radiation at the moment, and in the final part of this lesson we'll factor that in, because at the moment I just want to concentrate on my convection, my conduction, and my advection. And so if I think about non-dimensional groups here that might be useful, the Peclet number might be instructive at some point, advection to conduction. The BO number might be useful, external convection by internal conduction. And this will give us a feel for what's going on in this heat transfer scenario. But at the moment what I've got are these three modes of heat transfer, and sometimes one of these modes is going to dominate over the rest, so I may be able to simplify the problem quite nicely. Alright, let's think about boundary conditions. So if I'm thinking about the film between the die exit and my take-up rollers, then at the die exit I'm pretty sure I know what's going on. I'm going to assume the film is isothermal throughout its thickness and it's at the die temperature. That's probably a pretty accurate representation of what's going on. It's a little bit more circumspect what's going on around those take-up rollers. I need to think what my boundary condition is likely to be. Do I know what the temperature is there? Probably not. That's actually what I want to determine. So what could be going on? I could say that there's been enough heat transfer or sufficiently little heat transfer occurred for there to be effectively zero gradient happening there. It's like saying that at that point the film is insulated in my movement direction. It's not an ideal boundary condition, but at least it allows us to figure out what a temperature profile could look like. In reality, what's probably going on there is going to be a heat flux in the advection direction potentially, and we might need to estimate that. But if we estimate that there's zero heat flux to start with, it gives us a pretty good picture of what our worst case scenario is likely to be. Alright, so let's say that the full problem has convective heat loss from the film surface, the blue arrows, advection of energy due to film motion, the pink arrows, and conduction of energy within the film in either of the two dimensions that we've drawn the film in. Alright, so that's step one done. We've sat down, we've thought about the problem. Now we need to think about it a little bit more in terms of, well, what's happening inside the film? Is conduction really important? Well, let's see. Let's assume that we've got a polypropylene film. So now we're thinking about the material properties that the heat transfer is involved with. So if we've got a polypropylene film, we know that polyolefins have fairly low thermal conductivities. Let's say for polypropylene, my thermal conductivity is about 0.172 watt per meter per Kelvin. Okay. We've also got a film density there, 910 kilos per cubic meter, and a heat capacity, 2140 joules per kilo Kelvin. So ρ and Cp come to prominence when we think about advection. Let's put some length scales on this. Let's say that my average film thickness from top to bottom is about 5 millimeters. So it's as I said, it's a pretty thick film. It's kind of a thin sheet. What I'd like to do is to examine three different heat transfer cases that correspond to the extrusion process operating in different ways, or not operating as the case may be. So let's look at a very facile case to start with, which is where we've got a still film. Let's imagine that the extrusion line has halted. You've still got a hot die. You've still got some gradient condition at the take-up rollers, but there's no film motion. Let's furthermore assume there's no other means of heat loss. That convectum from the surface is just not present. That's a highly unrealistic condition. But I'm including it just to demonstrate that our mental model is actually a very powerful thing to do, because if there's no means of losing heat for case one, we don't expect there to be a temperature gradient. Let's go and mathematically prove that in a minute. The second case I want to look at is again one of a stationary film, one where the line actually isn't working but is at temperature. So let's say my extruder's hot, I've got this film, and heat is being supplied by conduction from that die along the length of the film, and that there's moderate heat loss by convection from the surface. But again, my film is stationary, there is no advection. The third case is when the extrusion line is actually operating. I've got a film speed of about 1 meter per second, we've still got convection heat loss with the same heat transfer coefficient from the surface, and we've still got heat conduction happening internally within the material. So those are my three cases. Let's think now what's going on in terms of conduction internally within the film for each of these three cases, and see if we can justify simplifying two-dimensional heat conduction to one-dimensional heat conduction. So we know we can use the BO number to do this. We can also look at the aspect ratio of the geometry. My film is long and thin. I might expect this to be a one-dimensional problem, but I also acknowledge that polypropylene has got a very poor thermal conductivity, so may want some numerical confirmation that my assumption is justified. So the BO number, the ratio of external heat transfer by convection, divided by the rate of internal heat transfer by conduction, HL over K. For case 1, H is 0. My BO number is 0. I've got a one-dimensional gradient, which is going to be in my extrusion direction. Remember that a BO number less than 1 means it's one-dimensional. It's just along the length. It's not in the direction of convection. BO number greater than 1, then there is going to be a temperature gradient in the direction the convection is happening as well. Let's look at cases 2 and 3, where I have a non-zero heat transfer coefficient. My BO number comes to be about 0.7. So I've specifically chosen the thickness of the material for this problem to give me the answer that I want, which is it's a one-dimensional heat transfer problem, because we can solve that analytically. Okay, so we sat down and thought further about the problem, and with use of the BO number and by looking at the aspect ratio, we can say it's a one-dimensional heat transfer problem. The key gradient is likely to be along the length of the film, not across the thickness of the film. And along the length of the film is, in effect, the extrusion direction. All right, and as you can see on the board, I have now removed the little red arrows that go in the same direction as convection, and that is my little diagram to say, yeah, I understand what's going on here. I've got 1D conduction. All right, so let's look at step 3. I'm going to choose my coordinate system, and I'm going to simplify the vector form of the energy equation into one that is more pertinent to this particular problem. So, we're dealing with a flat film, ideally described by Cartesian coordinates. Perfect. Now, where I am placing my axes is quite carefully chosen, because if I assume that the convective heat transfer magnitude is the same on the top of the film that it is on the bottom of the film, I have centerline symmetry of this problem. And if I place my x-axis on that symmetry line, that makes the maths a heck of a lot more straightforward, because on that symmetry line, I would expect there to be a turning point in a temperature profile, which infers zero gradient. And since I'm going to be solving ordinary differential equations, if I have a zero gradient at y equals 0, that's kind of nice to use. Okay, so I'm choosing my Cartesian coordinate system, and I'm being strategic where I place my coordinate axes. Okay, so let's write out the vector form of the energy equation. There it is on the whiteboard. In minus out equals accumulation. Let's look at each of these terms in turn and see if we can justify removing them. I have no heat sources on a volumetric basis in this problem. I'm assuming that at all times my sheet is molten. I'm not undergoing a phase transition. I am not undergoing crystallization. I am not putting energy transfer in by infrared that's being absorbed on a volumetric basis. So there are no volumetric heat sources. Big S subscript H equals 0. Let's now look at some of these flux-based terms. Remember, I've got my little control volume, and all these Q terms concern heat going across the faces of my little control volume. So, I've said there's no radiation heat transfer. I'm going to neglect that for now. We'll worry about that later in this lesson. Let's look at convection heat transfer. Well, for one case I don't have any convection heat transfer, but for two cases I do, and I know the magnitude of an average heat transfer coefficient, 50 watt per meter squared Kelvin. So I can write down that my convective heat transfer is going to be calculated by H A over V T minus T infinity, where T is the temperature of the film at the point along the x-axis, so T will vary with x. Okay, let's look at conduction heat transfer. I have already justified this problem as being a one-dimensional heat transfer problem because it's got a low BO number, less than 1. That means my temperature gradient is only going to exist along the length direction. So T is a function of X only because of that low BO number. This is a nice simplification. All right, let's look at the terms on the right-hand side. I'm going to assume this is a steady state problem, that even for those problems where there's no material motion, the extrusion line is stationary, that it has been stationary for long enough for there to be no time-dependent change of temperature. So that simplifies the problem further still, because we're not dealing with partial differential equations, where things are changing with time and position. We're just dealing with ordinary differential equations, where things just change with position. Okay, let's look at this final term, my advective term. Now for case 1 and case 2, I've said, look, the film's not moving. The extrusion line's stalled. The film is static. Case 3, however, we do have the film moving, and it's moving in the extrusion direction, so my x direction velocity in case 3 is not equal to 0. So the only non-zero velocity in that velocity vector, little v bold v, is Vx. The only gradient in the temperature gradient vector, grad T, is dt by dx, because we're just dealing with 1D heat transfer. So if we expand out that dot product, we've got Vx times dt dx plus Vy times dt dy, which is 0, plus Vz times dt dz, which is 0. So it's just Vx dt dx resulting from that dot product. So if we combine all these elements of simplification together, we get the following equation that I've put there on the board, which is a second order ordinary differential equation, because we've only got temperature varying with x. All right, let's identify some boundary conditions and start solving the problem. So there again is my little diagram of what's going on in terms of heat transfer. I'm now going to put my length and my thickness scales on there. And I'm going to say, look, at the start, at x equals 0, I've got a die temperature. So it's a specified temperature boundary condition. That's where the material's just left the extruder. That's at the temperature of the extrusion die. At length L, when x equals L, I'm assuming I've got an insulation condition, that there is no temperature gradient at that point. This is a slightly circumspect assumption, but we'll run with it for now, as it simplifies the problem and still gives us some insight. Okay, so let's think about case 1. There's no convective loss, the blue arrows disappear, and the film is completely static, the pink arrows disappear. So all we've got is heat transfer by conduction from one end, the die end, to where we said the temperature gradient is 0. Now there is no opportunity at anywhere along this film for heat to be lost. So therefore, we don't expect there to be a temperature gradient. We expect the temperature to be constant, just by physical reasoning alone. Let's now prove that. That's the answer we're expecting. Do we get it? So there is my energy equation, simplified to this particular problem. And we've said that H equals 0 and Vx equals 0. So therefore, all that's left is this equation, K d2t by dx squared equals 0. Which we can integrate twice with respect to our boundary conditions. If we integrate once, we see that dt by dx is a constant. Okay. Well, it's 0 when x equals L, so presumably then C1 equals 0. Let's integrate again. This gives us t of x is a constant. All right, well at x equals 0 we know what the temperature is Td. So our mental model is correct. The film is at a constant temperature. It's at the die temperature. There has been no opportunity for heat loss, so we wouldn't expect there to be a temperature gradient. This is why I've included this somewhat facile problem, because it illustrates how powerful the mental model is, and it illustrates the value of sitting down and thinking about things carefully. Okay, so we've got film at a constant temperature. Not a great deal of surprise there. All right, let's look at case 2. So case 2 was a little different from case 1 because we do now have external heat transfer by convection. And so those blue arrows come back again. We, however, maintain our static film. So this is corresponding to our extrusion line being shut down, but shut down at temperature. So our dye is still hot. We've got convection off the extrude as it's sort of lying there. And then we've got our rollers at the end. But the film isn't moving because, I don't know, the line stopped because there's an outage. So the advection term is 0, Vx equals 0, so the pink arrows aren't there. This is the benefit of a good diagram. We can clearly see what we're solving. My boundary conditions, I am assuming, are, however, the same. So let's have a look at the full equation that we derived from the energy equation as ascribed to our complete problem. And we can see that, okay, we do now have a positive heat transfer coefficient H. It's not 0, so we have to include that purple term. The pale blue term, however, involves advection, and we know our velocity is 0. So we can simplify that equation down to this second order differential equation thus, where we're balancing conduction and convection. Okay, let's think about what we expect to go on. We've got a hot end, we've got a 0 gradient end, we've got heat removal along the length, and we know that heat removal is driven primarily by the magnitude of the temperature difference between the film and the air. H, my heat transfer coefficient, is non-zero. So, for each bit of length along our film, I'm expecting heat loss. I'm expecting the heat loss to be bigger at the dye end than it is at the far end because my temperature difference is bigger. So I'm expecting a decreasing amount of heat loss along my film because the heat loss is being driven by the difference between the film temperature and the external temperature. So I'm not expecting a linear decrease in temperature because that infers that my heat loss is the same along the film. I'm expecting some kind of a curve. I'm expecting more heat loss at the start and less heat loss at the end. And when I get to the end of the film, I'm expecting to see very little heat loss at all because I've said my gradient there with respect to x is 0. So that is my mental model. That is really important to build. Let's see if the mathematics now prove that. Now, I can solve this ordinary differential equation analytically. There's an analytical solution that I'll go through the steps of. The full steps are in the document on Canvas. If I'm struggling with my maths, I can solve this symbolically within Mathematica. This can also act as a very good check for your own analytical solution. If I'm completely struggling, I can solve it numerically. This is usually what we'd be doing if we were doing a more complex heat transfer scenario and we'd simplified it to a point where we could try and compare it to something that we know about. More about that next lesson though. So let's look at the analytical solution to start with. So there's my differential equation along with my boundary conditions. The way to solve this analytically is to look very carefully at the form of the equation. What we're looking for here is an answer where the second derivative has a similar form to the variable itself. So the rate of change of t with x is kind of similar to how the second differential of t changes with x, isn't it? That's what that equation's saying. So let's have a look at making it easier. Let's create another parameter. Let's say capital theta is t minus t infinity. Let's group those terms together. T infinity is constant, so the second derivative of theta is just t. And so if script n there is HA over VK, that ordinary differential equation I've written there in blue, that second order one, is an exact same statement as the one at the top of the board. But it's easy to deal with. And so if I'm looking for a function that looks the same on its own as it does with its second derivative, it's going to be an exponential. We're expecting a curving decay of temperature. Maybe it's an exponential decay. So let's assume that capital theta is a times bx, a times the exponential of b times x. And to compare this to results you find in the literature, we can also remember that e to the x is the sum of two hyperbolic trig functions, cosh x plus sin x. So, without going through every step, the solution to that differential equation is as follows. You've got a temperature ratio on the left-hand side and a bunch of hyperbolic trigonometric terms on the right-hand side, which give us the shape and form of our gradient. The document on Canvas goes through that solution step by step by step by step. All right, let's say we want to check it. In this day and age, we can quite easily go to a symbolic solver and say, solve this differential equation symbolically for me. And if I go to Mathematica, the command that I'd type is there on the whiteboard. And let's just break that down a bit. So dsolve is a symbolic differential equation solver. The differential equation I'm solving comes first. T double dashed of x is simply d2t by dx squared. And then the remaining terms within that equation is that differential equation rearranged such that it is d2t by dx squared equals function of t. Next, I have my boundary conditions. So t dashed of L equals 0. That's dt by dx equals 0 at x equals L. And then t of 0 equals td. Well, that's simply at x equals 0, t equals t di. And if you type that into Mathematica, you get a lengthy expression involving lots and lots of exponential functions, which doesn't really look anything like the hyperbolic trigonometric function that we've derived. But remember, there's correspondence between exponentials and hyperbolic trigonometric functions. So let's compare the solutions by plotting them out. And if we plot the two solutions out, we get something that looks like this. The Mathematica solution is the orange dashed line. The analytical solution is the blue dashed line, and they're the same. Moreover, what this tells us is that our mental model was right. We've got our temperature decaying with length in a curvy manner, ending up in a zero gradient at the end of the film. There we go, so our mental model is right. This is the type and form of answer that we would expect. This is good. All right, let's revisit the solution step again, step 4, for the third heat transfer case. And remember, the third heat transfer case is when we said, look, the line is working, we've got the film moving, we have to take advection into account now. And so if we think about the equation that derived from our energy transport equation, we're now solving the full equation. We've got first derivatives in there, we've got second derivatives in there, and we've got the native variable temperature in there. Right, let's stop, let's think. We've got competitive heat transfer processes going on now. We have now in the mix advection. So let's just make sure we fully understand the influence of advection compared to those other processes, specifically conduction within the film. So let's work out what the Peclet number for this scenario is, because my Peclet number tells us all about the dominance of advection versus conduction. There on the whiteboard is my Peclet number written out, now with a number substituted into it, and we get a very interesting result. Advection utterly dominates the problem. We've got a Peclet number of 28,300. It's a bit bigger than 1, to say the least. So this means that actually heat conduction is negligible. So that second order derivative there, we can say is basically 0. And so that gives us another way to solve and simplify this differential equation. We can neglect conduction, and there I have on the whiteboard written out the equation that now corresponds to this advective heat transfer case. And now what I want to do is to sit and think. I've got a balance between advection and convective heat loss. My advection is big here. So let's think what's going on. I've got my control volume. I've got my film coming through that control volume actually quite fast. The film's coming out the extrude at the die temperature, and it's going to be losing a little bit of heat by convection as it passes from the die to the rollers. When it's static, I know I'll get a temperature gradient along the x direction. Equally, I can imagine I can move that film very, 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 very fast, and there's going to be no opportunity for heat to be lost. So a large Peclet number may infer, actually, I'm back to where I started again, and I might not expect a temperature gradient because the film is moving too fast for there to be significant heat loss along its length. All right, let's see what the mathematics says. I've got my first order differential equation there. I can solve it. It's a relatively easy one to solve. And I get an exponential decrease in temperature. All right. Perhaps not what I expected from my mental model. Or is it? let's just substitute in the physical properties and parameters that are specific to this problem. And if I do that, what I find actually is that at the film speed I've specified, with the thermal properties of polypropylene that I've used, convection cooling of when I've got a heat transfer coefficient of 50 watts per meter square Kelvin has zero impact. That film is hitting those rollers at the same temperature it left to die, which may give you some insight as to why chilled rollers tend to be used in film casting processes. Film casting processes run quickly. Natural convection cooling over small distances isn't really going to do anything. Okay, so let's summarize a few key points here. We've used our workflow now to solve the temperature profile in a film casting problem for 3 different heat transfer scenarios. The first thing we did was we sat down and thought about it, and then we sat down and thought about the problem a bit more still. We used dimensional analysis to help us really needle out what was going on here. We used the BO number first of all to justify a one-dimensional temperature gradient for all cases. When we came to dealing with an advective case, again we sat down and thought about it, and we looked at the Peclet number, and that allowed us to justify the complete neglection of heat conduction in that final case. 2 of the cases that we looked at, one with no heat loss, a very facile problem, and one with dominant advection, resulted in essentially an isothermal film at die temperature. That extrusion line shutdown problem, a static film but still with convective heat loss, allowed us to develop a temperature profile along the length of the film, and when we sat down and thought about what that temperature profile should look like, our mental model closely corresponded to the mathematical solution, yet again illustrating the value of sitting down and thinking about the problem before you solve it, constructing that mental model, and then comparing your mental model to the final mathematical solution that you get, and hopefully finding that they're the same thing.